Hello everyone, uh, welcome. So let's start with the next session on algebra. Okay, so we already had our previous session in which we discussed some of the problems on quadratics and polynomials. So this topic being quite wide in its scope, right? We have another session for today. Again with lot of problems which are quite relevant and pertaining to the kind of questions that have been seen. All right, so let's start. Here we go. Okay, so if first problem, if k is selected at random from the set of all possible natural numbers so that the equation x square minus 11x plus k equals 0 has real roots, then the probability that both its roots are integers is what, right, from the options. So how does probability come into the picture in quadratic? Well, we should always be open to questions which are uh, across multiple concepts, and actually probability is nothing but proportion, actually ratio of what is favorable to what is total possibilities, right? So here we have having k, which is a parameter which is involved in this quadratic, and we have to see the condition to be satisfied, right? First we need to find out all the possible values that k can take, and then the favorable values that k can take, right? So for the selection from all the possibilities, it is saying that it should be selected such that the equation has real roots, right? So all of us know what is the condition for the real roots. The discriminant should be greater than or equal to 0, right? So it's a very simple equation, quadratic one, with the coefficient of x is minus 11, the constant term is k. So what is the discriminant? B square minus 4ac. B means minus 11 whole square minus 4ac. A is 1 and c is k. So this is 121 minus 4k, which needs to be non-negative, greater than equal to 0, which means that 4k is less than equal to 121. And therefore that gives us, since k is a natural number, right? So k is less than equal to of 121 by 4, which is 30 and 1/4. So the highest integer that we can go for is 30 as per this limitation. And since it's a natural number, so therefore the set of all possible values that k can take goes from 1 to 30. So that becomes my all possibilities that we have. Now, so this being the total possibility, now the condition that we have to see is that probability that both the roots are integers. So the roots will always be real as long as k is in this range. But when will the roots be integers? That's the thing to now think about. Let the roots be alpha and beta. Okay, let the roots be alpha and beta. They are integers. What do we know about them? We know the equation is this. So we very well know the sum of the roots is what? Minus b by a, right? We know that alpha plus beta is minus b by a. So that becomes what? 11. So the roots are integers. Their sum is 11. So now we need to think that what kind of values can we implement over here such that k is also a natural number. Now what is k? K is nothing but the product of the roots itself, isn't it? So my alpha into beta, the product of the roots is k. K is a natural number such that it's the product of roots, and we know that the sum of roots is 11. Quite obviously the roots need to be positive integers only, right? So I can't have roots like minus 2 and 13 adding up to 11. That would make the product of roots to go negative, right? So we can only work in the positive integer domain, right? So basically it becomes that we need to break down this sum of roots in as many combinations as possible as the sum of two natural numbers, right? So the combinations of alpha and beta can be what? Starting from 1 comma 10. right? We can't even do 0 comma 11. Then the sum of roots will become then the product of roots will become 0. So 1 comma 10, k will take the value of 1 into 10, 10. Then 2 comma 9, product of roots becoming 18. Then 3 comma 7, then 3 comma 8, product of roots becoming 8 into 3, 24. And then 4 comma 7, again product becoming 28. So all these values of k are falling within the range of 1 to 30. And lastly 5 comma 6, when the two numbers are as close as they can get, and k exactly equals 30, the end of our range. So how many possibilities we have in the favorable zone? 1, 2, 3, 4, 5. So 5 values of k, which is these values 10, 18, 24, 28, 30, would make the roots to go as integers. So 5 out of the total 30 possibilities are favorable. So the probability is 5 on 30 on 1 on 6, right? So a lot of counting questions have been asked in recent years. So this question is that one involving algebra. All right, let's see next one. For how many integer values of a do the roots of the equation which is given below, x square minus a plus 1x plus 9a plus 3 minus a cube equals 0 differ by 2? So we have a quadratic in which the coefficients are all very in the variable form involving the parameter a, and some of the expressions are cubic in nature. You can see the constant term is like that. So something cubic is involved in a quadratic, right? Let's see. If alpha beta are the roots of this equation, basically the question states that they differ by 2. Means the magnitude of alpha minus beta equals 2, right? We have to find how many integer values of a will satisfy this constraint. Alpha minus beta is 2. Now, how do we deal with alpha minus beta value? Because what we can directly infer from any quadratic is the sum and the product of roots, but we cannot directly infer the difference. But through some manipulation, hopefully we should be able to reach there, isn't it? So we have that alpha plus beta is a plus 1 minus b by a, and the product of the roots alpha beta is c by a. So this much 9a plus 3 minus a cube, because the coefficient of x square is 1, right? Perfect. Now how to manipulate alpha minus beta and write an equation involving that? That's the first task that we have. So if we just square this, we can say that alpha minus beta the square is 4, right? Now remembering the fact that what is a plus b whole square and what is a minus b whole square, can I say that a plus, if a and b are any two variables, or let's say x and y, let me write x and y because I'm just stating an identity over here basically. So x plus y the whole square minus of x minus y the whole square, what will that give me? So x square plus y square, x square plus y square will cancel from both of the terms, and this will give me 2xy. This will give me minus 2xy, minus minus plus 2xy. So overall I'll get 4xy. So can I say that x minus y whole square can be written as x plus y the whole square minus 4xy? So that manipulation is required over here, right? So we can say that this is as good as alpha plus beta the whole square minus the 4 alpha beta, that is 4. Now let us substitute what we know over here, right? Okay, so a plus 1 the whole square minus 4 alpha beta, which is minus 4 times of 9a plus 3 minus a cube is 4. So simplifying further, a square 2a1 minus 36 of a minus of 12 and plus 4a cube is 4. So as I mentioned, this question will go into something called cubic, right? So now we have a cubic in the variable a to deal with, and that is why you can see the options are going up to 3, because a maximum of 3 possible solutions can go over here. But remember, we are looking to count the number of integer solutions for a. Now I'll be discussing a very relevant concept over here with higher order polynomials. Now look at this. We have that 4a cube, simplifying and collecting all the terms, 4a cube and a square, and 2a minus 36a would make it minus 34a, and this is minus 12 plus 1 minus 11 minus 4 is minus 15 equals 0. This is the cubic that I have. My objective is to find the number of integer solutions of this. Point number 1. Answer to this question can never be 3. We can reject that straight away. Why? Because the coefficient of a cube is not 1. If any polynomial, all the roots of a polynomial have to be integers, then the leading coefficient must be 1. For the simple fact that if all the roots are integers, it means that all the terms are expressed as x minus x1 into x minus x2 into and so on. So multiplying all such terms, the leading coefficient, the coefficient of the highest power of x would turn out to be 1. But that is not the case. Here it is 4. So clearly the answer option 3 is ruled out. We can straight away reject that. Second point, if this equation has to have any integer root at all, it can only be coming as a factor of the constant term. Once again, this is very important. Please understand. I'm just let me make some space over here. So what I'm trying to say, I think this is also done. Okay. So what I'm saying is that we are looking at a cubic and we're looking for the integer roots. Let's say the cubic is like x minus x1, x minus x2, x minus x3. So when you will expand, okay, when you will expand, the constant term will be the product of the roots, x1 into x2 into x3, right? In general, this could be, there could be a coefficient attached to x also. So it could be some constant here. Let's say a1 x minus x1, a2 x minus x2, a3 x minus x3. And this could be some constant here also. So a1x minus b1x1, a2x minus b2x2, b1x, b3x3, right? So when you'll multiply, you'll get something like b1 into b2 into b3 into x1 into x2 into x3. So that constant term, can I say, is containing all the terms involving the product of the roots. So therefore, if this equation has to have any integer roots, then it can only be the factors of this constant term 15, right, with a plus minus sign. So therefore, if you have to do hidden trial, my point is, if you have to do hidden trial with the cubic equation in trying to find the integer roots, you should only try that those numbers which are the factors of the constant term, because those are the only possibilities. So what happens is, if you don't have that logic, you will start trying very randomly. So you'll try plus n minus 1, then you will try plus n minus 2, then you'll try plus n minus 3. You'll go in a natural sequence. But the point is, here plus minus 2, you know that it can never be possible because of the fact that the constant term over here, right, is minus 15. So the only possible roots which could come here as integers could be factors of 15 with a plus or minus sign, which is plus minus 3 plus minus 1 also, and plus minus 5, and maybe plus minus 15, maybe, right? So therefore you should try only these. So let's do that. Trying 1, okay, we get, if root is 1, then at 1 it should be 0. So 4 plus 1 minus 34 minus 15 is not 0, clearly, so it's not a root. And even if you had tried minus 1, then it would have been minus 4 plus 1 plus 34 minus 15, that is also not 0. So plus and minus 1 are ruled out. Now let's try with plus and minus 3. Let's try 3. So 4 into 27 plus 3 square 9 minus 34 into 3, 102 minus 15. So this is 108 plus 9 minus 117. Yes, 117 minus 117. Yes, this is turning out to be 0. So we found our integer root, one of which is a equals 3. Now I can say there will be no further integer roots because I know that this cubic expression is a minus 3 into some quadratic expression. In that quadratic expression, the constant term has to be plus 5 to manage with the constant term of minus 50, minus 3 into 5, and the coefficient of a square has to be 4. So this kind of quadratic will never have integer roots because simply the coefficient of a square is not 1. There is no chance that this equation has any integer roots. However, sometimes on some occasions it could be possible that one of the roots is an integer. So for example, it could be such that maybe this quadratic is of the form 4a plus something and then let's say a minus 5. So if this quadratic has to have any integer roots, the only possibilities may be plus minus 5. So for sanctity of the problem at hand, just I should check quickly with plus minus 5 because that is the only possibility that could ever be an additional integer root because 2 is also a choice. So let's quickly verify for plus minus 5. If I put 5 over here, I get 4 into, I'm writing here 4 into 125, which is 500, plus a square, which is 5 square 25, minus 34 into 5 would be 170, minus 15, clearly not 0. It is something positive. And even if you try with minus 5, you won't get a 0. It will be minus 500 plus 25 plus 170 minus 15, right? So therefore, what is the answer? There's only one value of a, which is 3, right? So therefore, the logic to take care from now onwards is that in any cubic or higher degree order polynomial, if you are doing the hit and trial process to find the integer roots, you should only do that by by the factors of the constant term, right? And that's how we got a equal to 3 over here. All right, next one. So session is quadratic and polynomials, and today I have brought some very logical problems on higher order polynomials. The last one you saw, and again this one. So let's discuss. It is known that the function fx equals this: x raised to the power of 4 minus px cube plus qx square minus px plus 1 has 4 real roots. Which of the following is not possible for fx? So such questions, uh, they are very logical and they are testing our deep theoretical understanding of the topic, I would say. Now you don't have to solve anything here, right? You have something given, a function of fourth degree polynomial in which the coefficients are in variable form, and you have to analyze the possibilities of the roots. Options are like root 3 of the roots are natural numbers, 2 of the roots are irrational, 3 of the roots are negative. So which of these options is never possible? Means 3 of the options will be possible and the fourth one will not be. So to completely analyze each option. Now, the first thing to notice is the kind of symmetry in this polynomial that you have. You have minus px cube and you have minus px, the same coefficient. You have x power 4, you have 1. So the same number, coefficient is 1 here and constant term is 1 here. My point is, in this polynomial, if let's say alpha is a root, let's say let's say that f of alpha is 0, then due to the symmetry of the equation, it can easily be understood that if I replace alpha with the reciprocal of it, if I find what is f of 1 by alpha, that will also turn out to be 0, isn't it? If f of alpha is 0, then this expression is 0. Then what is f of 1 by alpha? 1 over alpha power 4 minus p over alpha cube plus q over alpha square minus p over alpha plus 1. If you multiply this equation, this expression, means if you basically take out 1 over alpha power 4 common, what you are left with is exactly the same equation that you had initially, which is 1 minus p into alpha plus q into alpha square minus p alpha cube plus alpha power 4, which is 0 to start with, because you're saying that f of alpha is 0. So this expression to begin with, you have taken to be 0, right? Just written in, just it is written in the reverse order, right? So this is the first deduction from the nature of the equation. So can I say that this must hold true for any root? What does that tell us? So if alpha is one of the roots, then 1 over alpha should also be a root. We know that all the roots are real and there are 4 roots. So the another root, let's say beta, is there. Then its reciprocal also should also be there. Let's say 1 over beta, isn't it? So that tells us that we have 4 roots which are of this form. They are reciprocal of each other. There are 2 such pairs of roots. With this understanding, now let's analyze the given options. Right, so this you had to deduce, only then we can further move with the question. So can exactly 3 of the roots be natural numbers? Can exactly 3 of the roots be natural numbers given that the roots are of this form? So we should try to make that happen, isn't it? We should try that. Is it possible? Even if one instance such we can create, then this option is not our answer, right? Because we are trying to make this happen. Well, one possibility could be I take alpha as 1, which means 2 of the roots get repeated, 1 and 1 each, which is quite possible because nowhere it is mentioned that the roots are distinct. It is only said there are 4 real roots. Does not mean they are distinct, right? So 1 and 1. And let's say I take beta as 2. So don't you think we have satisfied our option A? So that is not my choice, because it is possible for the 3 of the roots to be natural numbers, right? And the only way we can satisfy that is to make the 2 of the roots to be 1, and then the other third root to be a natural number, and the fourth root will become a fraction. So this is not my choice. Option B. Exactly 2 of the roots are irrational. Quite possible. Let's say alpha is root 2. Then the other root is 1 by root 2. So the 2 of the roots become irrational. Let the other 2 roots become rational. Let's say 2.5. So this is also not my choice. Exactly 3 of the roots are negative. Now this might be something which might get difficult to attain, isn't it? Because a number and its reciprocal are always of the same sign. So if alpha is negative, 1 by alpha is for sure negative, right? It means that either 2 roots can be negative or 4 or none. But 3 roots being negative, not possible. That's the correct choice. For sure, right? You have roots occurring in pairs. One is the reciprocal of the other, right? So either all 4 are positive, or maybe 2 of them are negative. Let's say alpha is -1 or anything, -2, anything, and beta is positive. Then 2 are negative, or all 4 could be negative. Exactly 3 roots being negative, never possible, right? Exactly 1 root, option D, yes. So that is also possible. So that is also not my choice. Exactly 1 of its roots is a natural number. Yes, that is also possible, right? For example, let's say we have 3 and 1 by 3, right? And let's say root 2 and 1 by root 2. So only one root is a natural number, quite possible. All right. So I hope this is interesting. Let's see, we have another very interesting question. Again, something to do with cubic. And now we are coming with a very different concept in this problem. Let's jump in. Let fx equals x cube plus px squared plus qx plus r. All the coefficients are in variable form except for the coefficient of x cube is 1. That is very good, what we know. Such that f1 equals f2 equals f3 equals 6. What is f4? Theta question. Okay, what to do here? There is something magical in this condition over here. The value of the function for 3 input values is the same, right? So you have to use that very intelligently over here, right? Here is what you should we can do with this. Can I say that if I define, let's say, an expression which is f of x minus 6, because I seen this number 6 being the value of the function for 3 values. If I just think of what would fx minus 6 look like as a cubic polynomial, obviously fx minus 6 is also a cubic polynomial. How should that look like? Can I say that fx minus 6 as an expression, let's put this in a box. So this thing equals 0 when x is 1 as well as 2 as well as 3, right? It means that fx minus 6 is a cubic polynomial whose roots are 1, 2, 3, isn't it? And how does a cubic polynomial whose roots are 1, 2, 3 look like? Isn't it going to be simply the product of the factors, which is x minus 1, x minus 2, x minus 3? So what do we conclude? Can't we conclude that fx minus 6 should be equivalent to, in the algebraic form, x minus 1, x minus 2, x minus 3, and apart from that, maybe you could multiply here with some constant also, let's say k. But I already know that my fx, the coefficient of x cube is 1. So can I say that I should let it be so that my coefficient of x cube retains as 1? So have I not written right now the equation of fx directly? That fx is nothing but x minus 1 into x minus 2 into x minus 3 plus 6. That is what fx is, isn't it? So very smart way to deduce the equation over here from the fact that the given function had an equal value for 3 values of x. So just take away that value, subtract 6, then what you should be left with is the product of the factors of fx, right? X minus 1, x minus 2, x minus 3. So this is fx. So what is f4? Now put fx equal to 4 in this equation. So what is f of x equal to 4? Just put 4. So 4 minus 1, 3. 4 minus 2, 2. 4 minus 3, 1. 3 into 2 into 1 plus 6. 6 plus 6, 12. Right? That is what fx is, and that is what is f4, 12. Right? So next time you see this, you know what to do. Okay, now we'll look at a few previous year problems. This is a ZAT problem 2023. Again, something to do with cubic. And some of the things that I have mentioned earlier will come into play. Let's jump in. The roots of the polynomial px equal to this are the radii of 3 concentric circles. 3 circles which share the same radius. The ratio of their area when arranged from the largest to the smallest is. Roots of this polynomial are radii of the circles. You have to find the ratio of the areas. So let's say r1, r2, r3 are the roots of this equation. They are the radii. So the ratio that we have to talk about is the ratio of the area. We know area of a circle is pi r square. So the ratio that we have to find is r1 square is to r2 square is to r3 square. Okay, so we have to just attack this polynomial, isn't it? We have to find its roots. And I told you that if you have to do hidden trial, try do that with the plus minus of the factors of the constant term. 6 factors are 1, 2, 3. So you should try plus minus 1, plus minus 2, plus minus 3. Let's quickly do that. Let's try x equal to 1. What happens? 2 minus 11 plus 17 minus 6 is minus 9 plus 11 is not 0. Right? And even if this was minus 1, at minus 1 this would have been minus 2, minus 11, minus 17, minus 6, which is obviously not 0. It is a negative number. So plus minus 1 ruled out. Let's try x equal to plus minus 2. Let's try first of all with 2. 2 into 2 cube 16, minus 11 into 4 44, plus 17 into 2 34, minus 6. 34 plus 16 is 50. 44 plus 6 is 50. Yes, this is turning out to be 0. Very nice. We have got x equal to 2. Now, the next thing that we have to do is polynomial division, isn't it? We have got x equal to 2 as the root. Right. Now we need to divide this polynomial with the factor of x minus 2, because we know that x minus 2 is its factor. Now I will tell you how to quickly divide, how to do the polynomial division very quickly. Right. Normally what people do is write the whole expression here, right? X minus 2 here, and follow the usual process of doing that ways. I'll give you an alternate way. Look at this. Look at this. Here is how to do polynomial division very quickly. You know x minus 2 is the factor of this cubic because you have identified that 2 is the root. Keep on writing the terms such that you keep on factoring out x minus 2. So you see 2x cube. So 2x cube you are seeing. So x minus 2, x into what is 2x cube? 2x square. So take out 2x square and in the bracket write x minus 2. So you have got your 2x cube. But this is mine, and now you're seeing minus 4x square, but this is minus 11x square. So minus 4 minus 7 is minus 11. So you should now write minus 7x square to match the next term, minus 7x square. Now again, minus 7x square you're seeing as the next term. So you should you should write minus 7x and bracket x minus 2, taking out x minus 2 as a factor, and you want minus 7x square to come there. So that is there. And now you are getting plus 14x, but you are seeing 17. So 14 plus 3, 17. So next is plus 3x. And now you can see that it is 3x minus 6 means 3 times x minus 2. I hope you understood what I have done. In each term consecutively, basically I have factored out x minus 2, and eventually I get the remaining factor, which are these terms: 2x square minus 7x plus 3. Right, 2x square minus 7x plus 3 and x minus 2. So this also should factorize because all options are in very nice integer form. So we are expecting some very nice roots over here. 2x square minus 7x plus 3. Yes, easy factorization. 3 into 2 is 6. So this should be written as minus 6x minus x. So 2x square minus 6x minus x plus 3. So we'll get 2x minus 1, 2x and bracket x minus 3 and minus 1 x minus 3. So 2x minus 1 x minus 3 x minus 2. Done. That was the only job, to factorize this cubic, and you were expecting roots to be at least rational, right? If not integers. All the roots were not going to be integers for sure, because the coefficient of x cube you see is 2. So therefore you can see this root of x equal to half is there, and then there is this root of 3, and then there is this root of 2. Perfect. So 3 is the largest, then 2. This is the ratio of the radii. R1 is to R2 is to R3. So the radii are 3, 2 and half. So the square, which is 9 is to 4 is to 1 by 4. That is R1 square, R2 square, R3 square. Multiplying throughout by 4, 9 into 4, 36, 4 into 4, 16, 1. Right? So option D, that's the choice. So yeah, hidden trial process has to be done in a logical manner. Right? I hope the logic is perfectly clear. You should attack the constant term. From there, you are able to identify the possibilities. Sixth one, CAT 22. If 3 plus 2 root 2 is a root of the equation ax square plus bx plus c equal to 0, 3 plus 2 root 2. 4 plus 2 root 3 is a root of another equation, but with the variable given as y, where a, b, c, mn. So a, b, c you can see in the first equation. In the second equation, you can see a, mn. So can I say this a is common? The leading coefficients are same in both the quadratic. Then you have to find the value of this expression b over m plus c minus 2b over n. Okay, so this question comes with a very important logic. All the all the coefficients involved in the quadratics are integers and your roots are irrational. If your roots are irrational and if your coefficients are all integers, it can only be possible if the roots are conjugate pairs, which means that if 3 plus 2 root 2 is a root, then 3 minus 2 root 2 should be the other root. So that quadratic which we are talking of, ax square plus bx plus c, should have its roots as 3 plus minus 2 root 2. Now, so you need to identify that quadratic, right? Now, what is the sum of the roots? Let's say the roots over here are alpha. Let's call the roots over here as alpha 1, alpha 2, and over here let's say beta 1, beta 2. Okay, so alpha 1 plus alpha 2 is what? The sum of these two will be 6, right? 3 plus 2 root 2 plus 3 minus 2 root 2. What is the product of the roots? Alpha 1 into alpha 2. So 3 plus 2 root 2 into 3 minus 2 root 2. Right? A plus b, a minus b. So a square minus b square. So 3 square 9 minus 2 root 2 whole square 8 is 1. So can I say x square minus sum of the roots 6x plus product of the roots 1 equal to 0 with its leading coefficient a is the quadratic. X square minus 6x plus 1 equals 0 has the roots of this, but I can also multiply throughout with a and that would also make it the equivalent equation. So basically that is what we have, ax square minus 6ax plus a equal to 0. Likewise for the second one, beta 1 beta 2, 4 plus minus 2 root 3, right? So the roots beta 1 beta 2 are 4 plus minus 2 root 3. So what is the sum? 8, right? 4 plus 4 8, and product beta 1 into beta 2 is, so 4 square 16, right? A plus b, a minus b. So 4 square 16 minus 2 root 3 whole square, so 4 into 3 12 is 4. So in terms of the variable y, we have to write y square minus sum of the roots 8y plus product of the roots 4 equals 0. Y square minus 8y plus 4 equals 0, multiplied throughout with a coefficient of a throughout. Right? Perfect. Now coming to what we have, right? So we have identified our quadratics, right? From the logic that the roots need to be conjugate pairs. Now the work is, the leftover work is just an easy cakewalk. B over m plus c minus 2b over n. Just write it carefully. So what is b? B is basically minus 6a, right? Look at this. B is basically minus 6a from the first quadratic. And m, so m is basically coefficient of y. Over here, this is minus 8a. So this a is basically cancelling off. It's a ratio, it's a fraction that we are finding. This a will cancel off. We are left with a constant number, right? This is 3 by 4. Plus for the next term, c. What is c? C is the constant term of the first equation, which is simply a. Minus 2b. Again, b is here, which is here, minus 6. Minus 2 times minus 6a, which will be plus 12a, over of n. N is this constant of the other quadratic, so that is 4a. Just finish the calculation. You have 3 by 4, and right, 6 by 3 by 4, and this is 13 by 4, so this is 16 by 4, which is 4. Perfect. 4. So you see, all the different logics have been asked in different ways, right? All right, let's look at a very interesting question that came in ZAT 2019, the last question for today's session. Again, I found this question to be very nice, very brilliantly designed. Given that a and b are integers and that 5 plus 2 root 7 is a root of the polynomial, you can see a quadratic x square minus ax plus b plus 2 root 7 in x. What is the value of b? All right. Now, your mind might be getting influenced by the question we did just now. In that question, the coefficients were given to be integers and we applied the logic that the roots need to be conjugate. Now, looking at the root 5 plus 2 root 7, you might get this inclination, oh, the other root should be 5 minus 2 root 7. But you know that the given quadratic does not have coefficients which are integers. The quadratic in front of you has the constant term which is clearly irrational, b plus 2 root 7. Because the question initially says a and b are integers, so b plus 2 root 7 is for sure an irrational number. So here you cannot apply that funda and you cannot say that, oh, the roots are 5 plus minus 2 root 7 and proceed. Okay, so how to deal with this problem? How to handle this? The most basic thing of polynomials or polynomial equations, the most elementary thing, factor theorem. As simple as that. If alpha is a root of the polynomial px equals 0, then x minus alpha is a factor of the polynomial and p of alpha equals 0. Right? So the most basic thing, 5 plus 2 root 7 when inserted inside this quadratic should make it 0. Yes, that is the meaning of the fact that that is given as a root, right? So we should write that equation and then let's see what we can do with that. Remember, a and b are integers. So let's put it. That's the only thing that we can do, and that is the only thing which can be said. So 5 plus 2 root 7 the whole square. I'm putting alpha equals this in this quadratic. So x square means alpha square means 5 plus 2 root 7 whole square minus a into alpha means 5 plus 2 root 7 plus b plus 2 root 7 should be 0. That must happen. Only then we say it's a root. So we have an equation in terms of a and b. Let's simplify. Let's expand everything and let's see what we have. 5 squared 25 plus 4 into 7 28, 2 root 7 whole square plus 2 into 5 10 into 2 20 into root 7. So 20 root 7 minus 5a minus 5a minus 2a root 7 plus b plus 2 root 7 is 0. Collect all the terms. So constant is 25 and 28, 53 and nothing else, 53. Let me mark what I'm writing. Collecting all the terms, minus 5a plus b. So I've collected all the numbers and now I'm collecting all the square roots. So 20 and 2. So 22 root 7 and minus 2a. So everything is done. 22 minus 2a root 7 is 0. Now what can we say? The sum of an integer and an irrational number is 0. This is an integer which I have written as the first bracket. This is an irrational number, root 7 multiplied with an integer, right? This can only happen if this thing, the number here is 0 and the coefficient of root 7 here is 0. Let me make it easy to understand. If I say x and y are integers, and if I'm saying x plus root 2y is 0, what values can x and y take? X and y are integers and x plus root 2y equals 0. Is there any other solutions for x and y except for x must be 0 and y must be 0? That's the logic, isn't it? If x and y are integers, and if this has to happen, then this can be the only way to satisfy this. So that is the kind of equation that we have, and that will help us get the value of what we need, right? So from here, 22 minus 2a is 0 means a is 11. 22 minus 2a is 0, a is 11. Put this over here. What is b? B is 5a minus 53, which is 5 into 11, 55 minus 53. So your answer is 2. Brilliant. All right, so that is what we had. I hope this was uh, interesting and enlightening. All right, so we'll see you again. Uh, do share with me your doubts, your comments, your suggestions, your inputs. I'll be looking forward to see in the comment sections. Ask me anything, right? And stay connected with us. Thank you so much. See you in the next one.